Okay, so welcome to the first quantized meeting of the new year, 2022. It's a pleasure this time to have Archana Kamal and just up the road from us at UMass Lowell, and then Hong, who's also just around the road from us over at MIT. Once again, this is now being recorded. Feel free to ask questions when the talk is over. Before the Q&A session, I will turn off the record after I will turn off the recording so that people can feel free to ask questions without needing to be recorded for posterity, if for some reason you're nervous about that. But anyway, so it's a particular pleasure to have Archana give us the first talk of the session on engineer open quantum systems. So without further ado, just take it away.
Thanks, Avian. I'm really thrilled to talk to this crowd. This is, I think, the first time I'm talking about our recent results in front of the consortium. So I'll start with a disclaimer. I think I overshot on the number of slides, so it's perfectly okay if I don't get through my talk. Just feel free to interrupt. So let me just right away tell about why we worry about engineered quantum systems. Of course, we know that when things are small, they are quantum. And of course, the classical mechanical laws do not apply to such systems. But of course, we want these systems to actually do useful things with these kind of systems, the quantum systems in the realm of quantum information. And that means that we want these kind of classical mechanical approximations or limits to fail for large objects. And that necessarily poses a challenge because the larger the objects get, the less quantum they become, and the main reason is decoherence. So the aim of engineered quantum systems actually is to beat decoherence. In fact, this article from, I think it appeared in Quantum magazine like 4 years ago, and it's still quite relevant. It said that the outlook is a bit cloudy for the era of quantum computing, and the primary reason it quoted as the primary challenge it quoted in this path to a quantum processor was decoherence. So that is basically our job when you think about engineered quantum systems. And I'll be talking about three main directions. They're kind of semi-independent, but of course, the idea is that here we are really considering dissipation or the openness of the system in a very meaningful way. These are all three recent results coming from our group. One is entanglement stabilization and autonomous error correction in open systems. Then how these kind of strongly nonlinear quantum optical systems, when subjected to dissipation, can throw us some surprises. And finally, this is something which is also in line with some of the other work being pursued in the consortium, how we can actually diagnose many-body correlations in the presence of dissipation or noise, because these kind of correlations manifest quite differently than Hamiltonian systems. So let me first start with the entanglement stabilization idea. This is actually the work which was also funded by DOE in a different program. So just for, I know that this audience is expert, but let me just start with a very brief overview. Whenever we think about open quantum systems, the reason there is decoherence is because the quantum system is not alone. It is actually always talking to some kind of uncontrolled degrees of freedom, which are uncontrolled either by construction or by circumstance. And these degrees of freedom we call Barth. And therefore, the evolution of the system is not just governed by the Hamiltonian, which is the first term, but also some kind of a non-unitary evolution for which we write, typically it's called a dissipator. And this is called the master equation. It's just a generalization of Liouville-von-Neumann equation. And the idea of beating decoherence up until now has been primarily focused on engineering the blue side, which is actually the system itself, or on trying to make it as pristine as possible, as isolated from noise as possible, so that the Hamiltonian dynamic, whatever we want to, if you want to do a collection of 1,000 gates, these are all unitaries. You can do them fast enough and in a perfect way enough before the dissipation of your system limits you, so that the evolution of the system to a very good approximation can be considered unitary. And there have been various approaches which people have adopted for that. For example, dynamical decoupling, the gate-based quantum error correction, all these kind of ideas are primarily based on trying to perfect the unitary evolution in some sense. And in the past decade or so, there has been this kind of complementary approach to Hamiltonian engineering, which is called quantum reservoir engineering, which it kind of turns the tables on the dissipation, which says controlled decoherence can actually help. So the idea is that, of course, we cannot control typically these large environmental degrees of freedom, but let us suppose that we actually strongly couple the quantum system to an auxiliary system. Think of this as an ancilla qubit, if you want, an ancilla system for which we can control. So that is still not part of the system because your information is still encoded in the blue bubble, but the kind of coupling which you are having between these blue and orange degrees of freedom is precisely controlled both in form and strength. And the point is to try to control this coupling in a way such that it works for us and in the asymptotic time limit, which means when sufficient time has elapsed, the system actually does or settles in a state which you want it to be. Hopefully, this is a non-trivial pure state. For example, an entangled state, which is what the aim of this talk would be, how we can actually use the system, dissipation seen by the system, to steer it into a non-trivial pure state. Instead of actually destroying coherence, can dissipation be used to actually preserve it? So the very simple way of thinking about these systems is to actually, again, as I said, we are not ever really interested in writing any description which does not pertain to anything but the blue bubble, which is the quantum system under consideration. So from a theory speak, what we actually think of this system as that there is a quantum system which is subjected to an uncontrolled dissipation, which is here I'm denoting with small gamma, and actually an engineered or an intentional dissipation channel, which I am denoting here as capital gamma. And when this intentional dissipation overwhelms the uncontrolled dissipation, this is the regime of reservoir engineering. Or the quantum reservoir engineering. And this idea was actually proposed by Sirac and co-workers, and then followed up by Zoller and co-workers in late 2000s, where they actually said that how collective dissipation as a resource can be used not only to stabilize states, but to even do meaningful quantum operations. Like dissipation can even, why can't you have a dissipative algorithm? The advantages of these approaches manifest because you're actually taking into account the dissipation of the system instead of perfecting a part of the evolution, which is what it is done in Hamiltonian engineering. So the prepared state is inherently stable over time. And in fact, these kind of protocols can be made completely robust to initialization errors, which is also nice, which means that irrespective of which initial state your quantum system is in, or either you don't really need quantum state preparation, because if sufficient time elapses, then this large gamma will ensure that your system reaches the intentional state. And of course, this is also inherently autonomous because you just arrange the dissipation and leave the system alone. So you don't actually have to do active time-dependent, active pulse engineering or very complicated unitary control. So in that sense, it's also is easy to implement. And because of that, it has been already demonstrated and employed in lots of QIV platforms like superconducting circuits, cavity QED, and so on. So what are how do we actually classify the steady states? Because so rho sub SS, when I say rho SS, it's actually the steady state of the open quantum system, which means this is the asymptotic time limit of the open quantum system. So in very heuristically speaking, and specifically for the point of view of reservoir engineering, one can think of the different kind of steady states in this two-dimensional plane, where the x-axis tells you how pure your steady state is, and the y-axis tells you how many steady states the system has. So for example, in the top right corner, these are called globally asymptotically stable states or gas states, where they are absolutely pure states. And there's also a unique attractor solution of your open system dynamic. So there's only one steady state and it's pure. And this is what we'll be interested in. And to achieve that, what you have to ensure is that the steady state is always an eigenstate of your Hamiltonian. And it actually is a dark state of your jump operator or your dissipator. So remember, this is the operator which is inside the D, the dissipative part of the evolution. If there are multiple jump operators, so that's why this is written for all K, then the steady state has to be a dark state of all jump operators. Similarly, if either of these conditions is actually this is violated, So either if it's not a eigenstate of the Hamiltonian or it is not a dark state of the jump operator, you can actually land up here where your steady state is actually, sorry, I think there's a question.
Yeah, I must have missed something. What are these jump operators exactly?
Sorry, so let me go back if I can. So these jump operators are basically the jump operators which are are introduced on the system because of the intentional dissipation.
Okay, so they're just operators that sit inside the dissipator somehow. And, okay.
A or sigma or something. X,
okay.
Whatever are you engineering? So this is the engineered dissipation operator.
I see. Good. Thank you.
The strength of the dissipation essentially tells you what's your gamma k, and the form of the dissipation which you're introducing tells you what is the jump operator. So yes, thank you for that question. Yeah, so these jump operators are basically the engineered dissipation which you are introducing. And so if you do not have either of these conditions satisfied, you'll actually have a mixed steady state. Then there is an interesting, this lower half is actually quite interesting, on both sides. One is the mixed multiple steady states. So these steady states are degenerate. They are degenerate in the Liouvillean sense, right? Because these are not degenerate states of the Hamiltonian. These are degenerate states of the full evolution. So the full Hamiltonian plus dissipative evolution can support multiple steady states. But because they are not satisfying, again, one of these conditions, they can be mixed. So I'm trying to show them as this bullseye on basically when you plot the Liouvillean spectrum. So actually I should have said that. What I'm showing is your Liouvillean spectrum. It's just like you have a spectrum of Hamiltonian, you can have a spectrum of the full Liouvillean map, which is telling you your dissipative evolution. And only the eigenvalue which sits at 0, whose real part is 0, is actually a tenable density matrix. So therefore, the only physical solution is what you find, what is the orange dot. And rest all these things are, of course, the spectral eigenvalues or an eigenstates, but they don't correspond to physical density matrices or physical states. So the delta is basically the gap. It's called, in some sense, it's the lowest, it's the eigenvalue, which is with the lowest real part. And that essentially tells you how far is your steady state removed from the rest of the eigenvalues. So we don't have to really right now know the details, but that is basically depending on how many steady states or how many 0 eigenvalues your system can support. That tells you the cardinality of the steady state. So here there are multiple eigenvalues which sit at 0, so you can get multiple states.
So is delta like an inverse time scale for relaxation or something?
Exactly, absolutely. So delta inverse is like a tau. Yep. And the final thing, which I'm not going to cover explicitly in this talk, but of course that is absolutely on our horizon, is to have multiple pure steady states. These are called decoherence-free subspaces, actually, where there can be an evolution within the decoherence-free subspace. So you can see there are multiple steady states which have a real, they actually have the real value as 0, but not the imaginary value. So in fact, these are the steady states of a Liouvillean, but they do have a non-zero imaginary part. So in fact, the evolution within this space actually looks like actually looks unitary. And this is essentially what happens when you try to do an autonomous error correction on a subspace of states, not just on a single state. So in this talk, I'll be focusing on basically the upper right-hand corner. I think there's a question again.
I just wanted to know going back to the lower right-hand corner, I mean, why can't you consider a mixture of those pure states?
So a mixture of the pure states lies here, because then your steady state is not pure if you have a mixture of pure states.
Right. So I'm wondering, if you're in the lower right-hand corner, what stops you from taking a mixture of those?
Because at every single point in time, this Hamiltonian actually so at every single point in time, they still are a dark state of your operator. So the important point is time t. Psi of t at any time t is actually a dark, it's a dark state of all your jump operators. But what happens is that it can have a non-zero imaginary part. So therefore, it's like we are back to a Hamiltonian physics in this case. So you never have a have a situation where you have a psi, like rho I plus rho j plus rho k divided by 3 kind of an issue.
Oh, so basically you can take mixtures, but in the lower left, you have to take mixtures. It's not so much that there aren't pure steady states, that there aren't mixed steady states in the lower right, but that there aren't pure steady states in the lower left.
Correct, exactly. Okay, so let us look at the simplest, and hopefully once I talk about the upper right corner, it will become more clear what's going on. So let us look at the upper right corner where we are actually trying to have at least a pure steady state, even though it is and it's unique, because that's the simplest case and still it's actually interesting. So as I said, the two conditions are that it has to be an eigenstate of the Hamiltonian and it has to be a dark state of all your jump operators. Because so that in some sense, once the system reaches there, rho dot is 0, it stops evolving, right? That is the steady state. Now there are two other conditions. First of all, you want it to be unique, which means the null space has to be one dimensional. There should be only one psi which satisfies both these conditions. And the other important point is that there are no subspaces of the Hilbert space which are completely closed under the jump operators, which essentially means I have to prepare this state. Not only, I don't want a situation where if I am in this state, I remain there indefinitely. I also want this to be a unique state of my dynamic, a unique attractor of my dynamic, which essentially means that there, at the minimum, there has to be some feeding channel into the target state. It can be like only one, but there has to be some connection with the rest of the Hilbert space and this state, so that I can prepare this and reach this from wherever I start in the Hilbert space. So that means that the target should belong to the right null space of the jump operator, but not the left null space. It should have a connection going into it, but not out of it. So let us try to actually see what is the most general jump operator we can write for, let's say, a 2-qubit system. Let's say I want to prepare a Bell state, which means an EPR state of 2 qubits. So what is the most general jump operator I can write? And I'm only allowing myself what is called local dissipation, quasi-local dissipation. Quasi-local dissipation means that at a time, I am only allowing my system to absorb or emit one excitation. So I can never have sigma 1, sigma 2 product. I'm only allowed, it can only be a sum of the, so this is called, because this is like linear dissipation. That's what happens in linear dissipation. Now, if I try this, very simple maths tells me, actually what happens is that alpha 1 has to be equal to alpha 2 and beta 1 has to be beta 2. If I try to maintain that, let's say I want to stabilize the singlet state, which is the EPR state. What I find is that the system actually has too many symmetries and the total spin actually commutes with both the Hamiltonian and the jump operator, which essentially means that if this is the total spin 1 manifold, and singlet has the total spin 0, neither the Hamiltonian nor the jump operator can ever connect it with the rest of the Hilbert space because it's conserved. The total spin is conserved. That means that I cannot simultaneously satisfy the fact that it is a dark state and also it has a connection to the rest of the Hilbert space. So if it means that I cannot satisfy these two conditions simultaneously, at least in a qubit space, just because the system has too many symmetries. So people have actually thought about this quite a bit. As I said, it has been one of the things which quantum physicists have worried about since 2010. They said, what if we don't stabilize the entanglement exactly? What if I stabilize a state which is maximally and almost maximally entangled? So let us say that I have a singlet with a very high fidelity and a very small error or perturbation on this, with some state phi, which is not singlet. And so this is called a symmetry breaking approach to stabilization, that we are introducing deliberately some kind of a perturbative error on the state in some sense. So for example, you can have some kind of a delta sigma z term in your Hamiltonian and you say, okay, let us try to stabilize this. Now what happens is this works actually. This does lead to stabilization of S, but there's a problem. First of all, as you can see, the error in the state, so steady state error, like how far am I from the intended entangled state, that actually grows with the impurity you have introduced. And at the same time, this impurity was why we had to introduce that, because we wanted a connection of the state with the rest of the Hilbert space. So the rate at which the steady state is prepared also scales with delta square. So this is a good thing which we want, that right? We want a high rate, but we don't want a high error. And that's what happens with this perturbative approach to state stabilization, that your error and time are anti-correlated. So it's kind of a trade-off that you have to wait for very long to prepare a very high fidelity entanglement if you use this, or you can do a very shoddy job very fast. So this was the main issue with dissipation engineering or quantum reservoir engineering of entanglement for quite some time. And we basically have done some work in our group where we actually have come up with multiple schemes, which we call exact state stabilization. So what is the meaning of exact state stabilization? That I'm trying to actually do a non-perturbative state stabilization of the maximally entangled state without breaking symmetry. But I have to also make a connection somewhere to the Hilbert state. So the very simple and actually intuitive idea to think about this is that we can actually extend the dimensionality in which we actually set up these processes. So let us consider, and what is the minimum extension of Hilbert space? Let's say instead of 2 qubits, I use 1 qubit and 1 qubit. That is the minimal extension, right? And I do that. So now I have a 6-dimensional space. And in this 6-dimensional space, the total spin is still conserved in this 4D space. So therefore, as you can see, there is no connection between these 3 states and the singlet state directly. But there can be a connection through the higher level, which in this case is the second excited state of the qubit. And if you do this, that means that you can have still a total spin conservation, which you require for exact dark state physics for singlet. But you can engineer a very fast preparation channel through the higher excited states. And again, this works with the linear dissipation. So this is the minimal instance to realize exact dark states with linear dissipation. And in fact, one of the main advantages of these kind of non-perturbative schemes is that since now we have broken this trade-off between error and time, because we are not using some symmetry breaking in the computational manifold, our error and time can actually scale together. So it means you can have actually very high fidelity state preparation in very short times. So as you can see, we call these, but it's not super important. We call these protocols peak or parametrically induced quantum engineering because we were using parametric interactions. But the more important thing is that the epsilon, it's not the product of epsilon times tau, which is constant. It's actually the ratio, which is now constant, which means they can scale together. But unlike the perturbative schemes where these were anti-correlated. So that is one very important advantage. The other thing is that now we can actually independently optimize different error channels. So here we actually find, this is a recurring theme which will happen in the talk, that the minimum achievable error or the maximum performance is always achieved when you balance dissipation versus coupling dominated errors. Right, so there's always a unitary term and there's a dissipation term, and it never. So basically, the point is, it never makes sense to make one thing very strong as compared to another. It's like the weakest link problem. You want everything to have a cooperative phenomenon. It's like a cooperative phenomena. So the unitary part and the dissipative part have to work together. And so, in fact, the minimum achievable error is achieved when kappa and g, where kappa is the dissipative rate and g is the unitary rate, are balanced. So this is what we call like the Goldilocks principle for quantum reservoir engineering. And in fact, all the authors which you see with the names underlined are actually students or postdocs currently in the group who have led this work. So in fact, just to assure that this really works, we actually did, with our experimental collaborators, we actually did this implementation of the qubit scheme. In fact, and we see that we can actually prepare singlet states, or in this case, triplet. You can choose whichever state you want. Any entangled state works. A triplet state with very high, reasonably high fidelity in 340 nanoseconds. But the more important thing is, as I said, the hallmark of exact state stabilization is that your error and time should be correlated. And that's what they were able to confirm in the experiments. And in fact, the slope of the line also tells you information about the local decoherence channels. It's not, I won't, in the interest of time, I won't go into that much detail, but I'll be happy to come back to this later on. And also, as I said, these schemes are extremely fast with very high fidelity. So we actually can come up with a cumulative performance metric where we you can think of this as a total badness metric in some sense, because you're multiplying the error in time. You want very small error and very short times. So smaller this metric, the better it is. And in fact, as compared to previous dissipation engineering schemes, we see around almost an order of magnitude to at least 5 times improvement. And we can also, came up with this, which I'm not going to discuss in too much detail. Again, if you're interested, I'll be happy to talk about it. How much E-bits you can generate, in some sense, average information generated per bandwidth per bit per time. And what we find is that this kind of scheme actually leads to around 6.23 number of E-bits per unit bandwidth per unit time, which is at least, again, at least double than the nearest competitor in some sense. So are there any questions on this part? If not, I'm going to go to the second part of the talk, which is actually multi-photon nonlinearity and dissipation, how this plays in. Again, yes, there is a question.
Yeah, so my question is it just for specific states that you can do this? Or could you say, like, I don't know, take the ground state of some complicated Hamiltonian and engineer this dissipative system that brings you to that state?
That's a very good question. So in principle, it can be done for any state. The point is that, of course, if you want these techniques to be adopted in any kind of a realistic implementation, the many-body Hamiltonians, in fact, we're thinking about this right now. Can we use it to actually have the ground states of quantum annealing, right? Like, can you do dissipation engineered quantum annealing? I think the point is as long as you can write down your dissipators in some kind of a quasi-local or semi-local form, then yes. It doesn't make sense to actually keep increasing the number of the depth of the operator which you are writing for many-body Hamiltonian. So the challenge is not that they can be done. The challenge is to do them with semi-local interactions, which is what the aim is, because it's very hard to generate, n-body interactions. Like, so here as I was saying, I only am using local quasi-local or linear dissipation. You can use nonlinear dissipation, but maybe you can have like O1, O2, but that's about it in terms of what experiments can do. So even theoretically, it doesn't make much sense to actually write down n-body operators, because then you really are not dissipation engineering. You are just like getting lost in a exponentially large Hilbert space. So, okay, please put your questions in the chat, because sometimes I'm not able to see the chat. So I'll be on, if you can have an eye on the chat, you can just read the questions. But okay, let me go forward with the next part of the talk, which is multi-photon nonlinearity and dissipation. So let me introduce the system. This is actually a very interesting system. It's a superconducting circuit system, which is one of the major platforms whom we collaborate with. So this is actually again actually an array of Josephson junctions, which have some capacitive coupling to the ground, and it's this assembly is actually called a superinductor. And it's not called superinductor because it's made of superconducting circuits. It's called superinductor because the impedance of this system at RF frequencies is greater than the resistance quantum, which essentially means it really behaves very much like an inductor, where flux is a good quantum variable and charge fluctuations are completely suppressed. So this is actually, if you want to think about this as a metamaterial, here the inductance comes because of the winding of the wave function of the superconducting wave function. It's not coming because of some geometric inductance, because geometric inductance can never violate this bound of having an impedance greater than the resistance quantum. But here, because the underlying mechanism of inductance is actually kinetic inductance of the superconducting wave function, it can actually achieve mu, if you want, the permeability of 10,000, which is absolutely impossible with any other naturally occurring inductor. So it's a it's fine if like we can talk about superconducting circuits offline, but the main point is it has a many body complexity, because if you think about if you can think of each of these Josephson junctions as an independent degree of freedom, which are all coupled together and they're highly nonlinear. So it actually leads to a highly nonlinear many body coupled system with tolerance to dissipation, at least at DC, because it's made of superconducting elements. And as I said, these are Josephson junctions are highly nonlinear circuits. So they have very, very strong intermode coupling, which means that perturbative treatment should not work to describe the system. So we actually characterize this system. The experimental collaborators actually characterize the system, and this is the way they actually read out the system. This is called dispersive readout. Again, details are not important, but the main point is that they can actually chart out the dispersion relation of this multi-body system, or if this chain of nonlinear atoms, if you want. It's like a 1D chain of atoms, and this is what the dispersion relation actually looks like. Where the largest frequency is actually set by what is called the plasma frequency of each atom. And this is what the response of this system actually looks like as a function of detuning. So this is just a driven response of the system, where we are actually counting what is the number of photons in a given mode as a function of the detuning of where the system was being driven. And now if you look at this, the more you look at this plot, the less it makes sense actually. Because think about, so let me explain why it doesn't make much sense. When we first looked at this data, it made zero sense. Because as I'm increasing the drive power, if it is really an oscillator, a very highly nonlinear bosonic mode, which is how we think of these things as in these these kind of dispersion relations, this is like a bosonic mode. There is no increase in the amplitude at a given frequency, no matter how much drive power I put in. It's a multi-mode system. It should be behaving like a bosonic system, but it actually has a frequency selectivity of a qubit. In a qubit, if you drive a transition hard enough, you can just saturate that transition, and that just makes it wider and wider, which is what seems to be happening here, except for this weirdo line shape. But no matter how much drive power I throw at the system, I can never actually have a build-up of the population in the system at a given detuning. So it really is somewhat like in the middle of an oscillator and a qubit. And in fact, this is the kind of like map we actually developed to understand the system. If you think about this, the qubits lie here, or like let's say an atom lies here, where depending on, you have a very large nonlinearity. And so very few levels, like few level systems. And the photon lifetime is very high, because of course qubits are very coherent objects. So they have a very few peaks, and the more power you actually put in, you start exciting higher order transitions and so on. So that is what a qubit spectrum looks like. This is what a nonlinear oscillator actually looks like. This is called a Duffing oscillator, as many of you may know. This is a classical nonlinear oscillator, where the more population you put in, it just because of the nonlinearity, it shows back bending and hysteresis. This is a truly multi-level system. So there are lots of levels, but it's not very coherent. So the photon lifetime is very low. That's why it is in this corner of the graph. And this system, the superinductor, actually lies somewhere in the middle, what we call a meso system. In some sense, it has some features of both these extreme ends. It has many levels like a bosonic system, but every level has very few excitations like a qubit. Because as I showed you on the data, no matter how hard you drive, you cannot really go beyond a given n bar in a given mode. So in some sense, and if you think about nonlinearity over dissipation axis, this superconductor, superinductor actually lies somewhere in the middle of a completely macroscopic oscillator and a two-level qubit. So we wanted to really understand what's going on with these kind of systems, and especially how dissipation manifests in this mesoscopic regime, where you do have many levels, which are reasonably coherent, but you cannot really populate them beyond a few photons. So this is just a very brief map of what happens in a non-equilibrium quantum system. So if you look at these lines, this is actually called a switching dynamic. So you actually are trying to populate the oscillator. It leads to a large photon number, and suddenly it switches to a low photon number. So in fact, this is the example of the multiple steady states. There is a low photon number state and there's a high photon number state, and there is some kind of a switching between these two things. So these switching dynamics in the non-equilibrium quantum systems actually can happen in multiple ways. So in the non-equilibrium quantum systems, you have to actually think about quasi-energies. And because of quantumness, the quasi-energy of the final state actually in these systems can be greater than the initial state energy, even at zero temperature. This is a truly quantum effect. So the actual energy always decreases. So there is no violation of thermodynamics. But the quasi-energy of the system can increase because it's actually a driven dissipative system. So it's not really surprising. And the way the system actually switches out of a given state or does state transitions, there are three types. One is it can always relax. The other option is it can actually diffuse over the barrier. This is called quasi-energy diffusion. And the other option is, of course, to quantum mechanically tunnel across the barrier. So these are the different mechanisms of actually having any kind of dynamical relaxation process in non-equilibrium quantum systems. Now, even within the quasi-energy diffusion, there are two mechanisms. Either it can happen, this kind of diffusion can happen due to thermal fluctuations, which means thermal fluctuations lead you to the hopping over the barrier. Or it can be what is called a quantum activation, which is kind of a semi-classical model. It's extremely successful, and it is actually used to explain reaction kinetics even in quantum chemistry, where you have a diffusion over the barrier, but it is because of quantum fluctuations. So the fluctuation magnet energy is not kBt, it's h bar omega. So this is actually semi-classical because there is no real tunneling, but you still need quantum noise, at least as a source or a driving term. So if I try to plot dominant dynamics as a function of temperature of the system, in high temperature, I always see thermal hopping over the barrier. So in some sense, if you think of this RNA's escape law, this is some kind of an attempt frequency in the pre-factor. Kappa is my dissipation. The omega B is essentially actually the instant on frequency, which is below the, if you have a flipped potential, what is the frequency of the inverted potential. But the more important thing, these are just pre-factors. The more important thing is the form of the exponent. And in the high temperature limit, the exponent scales as the barrier height over kBt, where kBt is the thermal fluctuation energy. In the quantum activation over the barrier, which means there is a quasi-energy diffusion over the barrier, but because of quantum fluctuations, it's VB over h bar omega. And in fact, this order one prefactor is also very well understood. It's a very strange value of 7.2, but that's not super important for our purposes of discussion. But the main thing is it's h bar omega, not kBt, which tells you what is the temperature of the fluctuations. And finally, within the low temperature regime, there is a crossover from quantum activation to quantum tunneling, where you cannot just do the semi-classical approximation of just adding quantum fluctuations as a driving term, but you actually need need to really think about this gap physics, which is what I showed in the Liouvillean spectrum, and you actually have to do a full quantum treatment. And this is where we think that tunneling really dominates the dynamics. So basically, cutting the long story short, we actually analyze the system to see, can we actually explain the switching rates? And we found that the quantum activation explain the escape rate in the mesoscopic regime? Because ultimately, we are still multi-level physics. Can quasi-energy diffusion in this multi-level strongly nonlinear systems be explained? And the answer is no. And the reason, and in fact, we found that in the weak nonlinearity regime, the semi-classical model is very nice. But as soon as your nonlinearity over dissipation becomes of the order of order unity, like 1 or 2 or 3, you actually have to already resort to a fully quantum treatment and quantum activation, or ad hoc addition of quantum fluctuations does not work. So why is that the case? Because in this case, dissipation is not strong enough to actually have the system in thermal equilibrium even in steady state. It's really, in some sense, remains out of equilibrium all the time. So you can have, this is truly a non-equilibrium steady state issue, that if you look at the quantum trajectories of the system, they never really settle into one of the metastable states. And in fact, based on this, again, in the interest of time, I'll just go a little fast. Based on this, we were able to actually define a crossover parameter, if you want a phase, an order parameter to actually see this crossover from the semi-classical to quantum regime. So here, as I said, at T goes to 0, what sets the temperature of the fluctuations? It's the dissipation. Now that sets the temperature of the fluctuations. So you define a dissipative temperature. And then you define a tunneling temperature, which is set by actually your gap physics, your non-linearity strength, your number of photons, all the unitary dynamics. And in the regime where your tunneling temperature is higher than the dissipation temperature, which means your dissipation is unable to establish a thermal equilibrium, that is when the fully quantum treatment is required. So in some sense, this seemingly simple looking system, that's chain of atoms, is able to actually show us some very interesting quantum, classical to quantum crossovers. So this is the end of that part. Are there any questions on this part? Because then I'll go to the last part of my talk in the last 15 minutes or so, and go from there. Any questions? Well, if not, let me just go through many-body correlations in open systems. I think this should be of interest to people who are anyway working about entanglement characterization. So what is a problem statement when we think about many-body correlations? The problem statement is we have d-dimensional systems typically, be it field theory or atoms or condensed matter systems. And they are very strongly correlated. They are n-body correlations. So the Hilbert space is very large. It's d to the power n. But we want to characterize these kind of correlation or these kind of states with very low weight observables. This comes back to the earlier question of like, can we do condensed matter physics, dissipation engineering? And the answer is yes, but we want to generate them and characterize them. In some sense, the generation and characterization complexity should be M local, where M is much, much smaller than M. Because we, like, for example, if I have a collection of large number of qubits, ideally, I would like to measure only 2 qubit observables and characterize my n-body state. That is the problem statement, that we want like quasi-local observables to actually characterize these very large correlations. There's a lot of motivation to do this from various sides, like cosmology, condensed matter, and quantum information, of course, because there are exotic phases of matter, like the toric code itself is an exotic phase of matter. It's called a string net liquid. And this is actually a crystal called Herbert-Smithite. So I guess you can probably guess who discovered it. It was Mr. Herbert Smith. And it's the ground state of this crystal is actually an antiferromagnetic Ivy lattice. It's a spin Hall liquid. So to actually characterize these kinds of very exotic ground states of systems, we again want to do this using some kind of a semi-local observable. Of course, we also, there's these really interesting results which have come recently, which have shown that especially when you do these kind of characterizations in open systems, which can support mixed states or mixed state entanglement, they can be arbitrarily more non-classical than pure state entanglement. So, so there's a lot of motivation to do that. Unfortunately, the current state of the art to actually have very reliable entanglement witnesses is extremely primitive, because the necessary and sufficient criteria only exist for 4 and 6 dimensional systems. I mean, there are criteria where you can, which works with sporadic success for larger systems, but in terms of actually having a smoking gun, we actually can only characterize very low dimensional systems. Moreover, witnessing noisy entanglement or mixed state entanglement is computationally hard. In fact, it is NP hard. It could be as hard as 3-SAT problem to get an accuracy, which is 1 over the polynomial in system size. I think Vijay, you have a question.
Yeah. 2, what does it mean to be arbitrarily, or how do you define what something means for something to be non-classical as opposed to classical, as in what does that mean? And also, there's also a nice note by Paul Ginsberg about Herbert-Smithite, and I was going to ask about that too. What is Herbert-Smithite? I've never heard that.
It's actually a very complicated, I don't remember the formula. It's like zinc, copper, oxygen. It's like a very complicated oxide of sorts. And it's exactly a crystal. If you like, and it has a lot of brilliant, like green, shiny properties. But the main thing is its ground state of that is actually a quantum spin liquid.
I see. Paul, just give us the formula.
So because it has a very complicated crystal structure, so that is the only ground state which actually emerges in this particular combination or stoichiometry of elements it has. I should have included the chemical formula. It just made no sense to me, so I dropped it. But yes.
So how do they know that it's ground state? It's a quantum spin liquid. It's a measurement in some.
They know that it is a Kagome antiferromagnet, and they basically do some kind of a they have actually done some very sophisticated numerical simulations for this, and this is actually the speculation, I would say.
Yeah, my reaction to the people finding materials like this is just like my reaction to how does, tribe X in somewhere in India know you can eat random berry Y, right? You have to try so many of them to find it. But anyway, okay, wow, cool.
Actually, I think Paul Ginsberg just put the formula. So yeah, it's just something, right? Yeah, it's very complicated.
There's a paper, Herbert Smith, in Search of the Quantum Spin. Like, okay, fine.
Yes. So, but that is the motivation of quantum material scientists, because they're actually naturally occurring materials which we don't know how to even write a wave function of. So let me. I think this comes back to Vijay's question that why is it hard to characterize? I think there's a question by Veronica.
Oh, I was just going to re-ask the other question that Vijay asked, which is, what does it actually mean to be arbitrarily non-classical?
Yes.
You're getting to it.
Yeah, let me actually go to the next slide, and if I don't answer your question, then you should answer, because it's actually a hard question. I don't know if I'll be able to answer it to your satisfaction. So let us basically try to understand, what does it even mean to characterize noisy many-body correlations? Many-body correlations anyways are hard in unitary Hamiltonian systems, but in noisy systems, what does it mean? So for pure states or noiseless states, unitary, evolution, everything, quantum correlations mean entanglement. It's one and the same thing, right? We say entanglement is quantum correlation. But for mixed states, there is a broader class of quantum correlations. It's not just entanglement. Because entanglement in some sense is a superposition in the tensor product space. Whereas in some sense of quantumness, and this comes from what do I mean by arbitrary non-classical? In quantumness is a more general idea than entanglement, because it is when I say quantumness, it means non-commutativity of observables, which means if I try to write down, for example, a matrix product or an operator level description of a quantum state, then the operators which are entering in the description are non-commuting, because this is directly related to the measurements. So in some sense, the noisy quantum states support a bigger class of correlations than unitary or noiseless quantum states, because there can be, like, for example, quantum discord. Right? There are states which can show quantum discord even though they are mixed. So a finite quantum discord can exist. So that's what I mean by arbitrary non-classical. In fact, there were these recent, it's not recent, it's 20 years almost now. There was this very interesting paper by Josa and Linden, who said that to achieve exponential speed up over classical computation, the unbounded growth of entanglement with system size is required, which means that more entanglement is absolutely necessary if you want to really have exponential speedups, because everyone is searching for the next Shor's algorithm if you want. But they also speculated in the same paper that maybe exponential computational speedup might be possible even without entanglement if you allow yourself mixed states. And the reason for that is to describe mixed states. In some sense, if you one way to think about it is, what is the level of complexity I need in my description to describe a given state? And the more complex the description, it's a quantum complexity argument. The more complex the description, the farther away it is from classical, and more likely it is to have some kind of an exponential speedup. Or at least it has a hope of giving me something which is not classically achievable. And mixed states actually fit that criteria, that they are actually some can get exponentially complicated to describe and characterize, which is why it is so hard to actually witness noisy entanglement. So it's basically a quantum complexity problem. I'm not sure if that answers the question, but that is the rough idea of why we think they are arbitrarily more non-classical, because there are even more classes of correlations which we don't even know how to characterize.
So just to follow up, then there might be some upper bound to this quantity, but it's much maybe exponentially larger than.
Yes, that is the hope.
Okay.
Yes. So how do we actually characterize noisy multimode correlations? So again, we start with our the master equation, and we know that is exact solution. So ideally, what we would want to do is to exactly diagonalize the Liouvilleans. But the problem is exact diagonalization of Liouvilleans, which I was actually trying to show you in the first half, become exceedingly almost impossible to do because of your large system size. In fact, a Hamiltonian is an n-dimensional object, and a Liouvillean lives in an n-squared space, right? Because it's a density matrix. So n-squared dimensional objects, so it's like 2 to the power n squared. There's no way we are going to ever do that, right? So exact solutions of Lindblad master equation are anyway hard, they're not forthcoming. So we have to come up with a way to actually characterize these things without actually resorting to exact diagonalization techniques, because they are not happening. So there is one way of actually going about this and trying to reduce the system to Hamiltonian level complexity, where you take the Lindblad mechanism and post-select on all the trajectories which have no jumps. So this leads to what is called the non-Hermitian Hamiltonian. So what does that mean? That means that you basically, when you expand the dissipator, typically Lindblad dissipators look of this form. You throw away the jump term. The red term is actually ignored, and the remaining term describes what is called a non-Hermitian effective Hamiltonian. So it's a non-Hermitian object. It's a weird object because it's a non-Hermitian Hamiltonian. But basically, it's not that weird, because the only part it is missing is the jump part. Well, it's a very important part it is missing, but it's missing the jump part, but it does tell you about the width of the levels. So these are the energy, the gaps between the levels, and this tells you the width of the levels. So now H effective by itself typically is not diagonalizable, but there is a possibility to do singular value decomposition of the H effective dagger H effective, this operator. Albion, you have a question?
No, I got it. Thanks.
Okay. So the point is to actually try to look at eigenvalues of the non-Hermitian Hamiltonian. And these actually can correspond to or give us a good indication of even the Liouvillean spectrum, even though we are not diagonalizing the Liouvillean directly. But this actually tells us what is the kind of degeneracies we can expect. So one of the things which people have actually tried to do this with these non-Hermitian Hamiltonians, sorry, there's a question, I think.
Yeah, it's just counterintuitive to me that it could be possible to get an exponential speed up using mixed states without a lot of entanglement, when you couldn't do it with pure states without a lot of entanglement, because the mixed states are just like classical mixtures of pure states. So
yeah,
I would think that the mixed states wouldn't really give you any more power than the pure states, because if you like, all they are just sampling pure states with probabilities.
Not really. Actually, mixed states can give you non-zero quantum discord. So there are other kinds of quantum correlations mixed states can support. And the main point is it's not some arbitrary mixed state where you just have a, not the mixed state of a qubit. That's of course trivial. But when you think about mixed states of these really largely correlated systems, these are actually exponentially hard to describe. Just because mixed state, I mean.
Well, the dimension of the vector space is the square of the.
Because in some sense, yeah, one way to think about it is mixed states cannot, like at least a psi can be written in a, as a tensor product space in some sense, like there's a Schmidt decomposition in some sense.
Okay.
It simplifies it. For mixed state, that doesn't exist.
But you could always write the mixed state as just some.
If you know the good basis to write a mixed state, then we don't even know what is a good basis to write these states for large systems.
Maybe I can add also, you might not be able to track it through the computation. So it could be that you initially have a separable state in some convex combination of pure states, then you do some noisy gate, and then it's still a convex combination of pure states, but you might not be able to find that efficiently from the decomposition you had before.
Thank you, Aram. That's a very good point. Yes.
Well, couldn't you use like some quantum trajectory thing where you just sample those pure states with the appropriate probabilities?
Well, if you can do an exact simulation of a very large system, yes. I think I'm not sure how tractable those are typically to actually track the full state space.
No, I just mean that you can think of it as statistically sampling those pure states that you
Yes,
study.
I mean, it is true. But you need a go ahead.
Well, but those pure states can become very entangled. So even though the state overall is a mix, is a separable state, that only means there exists a decomposition into product states, not that you can easily find it. So you start off with product states, a mixture of product states. You start doing some entangling gates. Like take the maximally mixed state, right? Completely mixed. Then you decompose it into computational basis states, and you start tracking it through your computation. It gets super entangled.
So my initial
trajectory can be harder. Make it harder.
Is something like, something like that, and then maybe like if I evolve this unitarily, that can like lead to entanglement in these terms. I see what you're saying. Okay.
We can, of course, come back also to this question, but let me just move forward for the time being. But yeah, thanks, Aaron, for all the clarifications. Those are all on point. So yes, so the point is to actually use these non-Hermitian generators, which actually do not know about quantum fluctuations because we have actually eliminated the jump processes completely, but we have retained the widths which these vacuum fluctuations give to each level, which is the meaning of non-Hermitian Hamiltonian. So now using these non-Hermitian Hamiltonians, people have actually worked with things. Can I take 5 more minutes because I'm actually not, yes. Okay. So because the point is this, so they find what are called exceptional points. These exceptional points are basically degeneracies in open systems. So whenever the open system eigenvalues become degenerate, we say that there is an exception point. And the number of eigenvalues becoming degenerate tells us what is the order of that exception point. So EP2, EP3, EP4, and so on. So let us say that and at these exceptional points, it's kind of interesting. For unitary systems, when you have a degeneracy, your eigenvectors remain orthogonal. But in open systems, when you have an exceptional point and your eigenvalues become the same, your eigenvectors become parallel. So these exceptional points are really very special points where your generator is not even full rank. That is why you have to write a Jordan normal form for your Liouvillean and so on. So but the more interesting and physics part of it is that these exceptional points have a very nice experimental signature that they lead to normal mode splitting of your spectrum. So when your things become hybridized, when two systems become hybridized, their spectrum is no longer single peak, they actually show multiple peaks, and the number of peaks correspond to the number of systems getting hybridized. And it has implications for several applications such as quantum ground state cooling. So imagine that you have your quantum system, which I'm showing here with the A1, and you strongly coupled it to some auxiliary bath, and that bath is decaying at a very, very fast rate. So what you want this system A1 is to cool down to its quantum ground state. So you want to shuttle all the excitations into the bath, and those will decay through the bath. Now, this actually has been adopted again in lots of cool oscillators, including, starting from almost 15 orders of magnitude variation. This is a very standard technique. It's like a quantum refrigerator if you want. But the point is that in the place at which the population starts saturating is the place where instead of this, as you increase the coupling, what happens is as you keep increasing the coupling, instead of shuttling the excitation starts Rabi flopping between the two modes. Because the G is so fast as compared to the decay rate or the dominant decay rate of the channel, that it just leads to oscillations between A1 and A2. And that's when the population just saturates. And in fact, this crossover is captured or described by an exception point. So what happens, we actually asked the question, can we actually do ground state cooling with correlated baths? That's essentially originally was was our aim. And let's say I actually have correlated bars. So system doesn't know that I have cheated and I have actually multiple bath correlations talking to it. And then what happens? When we plotted the population curve, we actually found that we were not able to see any crossover. And that makes no sense because eventually when I keep increasing the coupling of the system to its bath, no matter how correlated the bath, eventually I should see some kind of degeneracy develop and some kind of exceptional point normal mode splitting. So we actually extended the problem and we said, okay, we don't even know how to actually go from weak to strong coupling in these systems in the most general way. We considered a 1D chain of these bosonic systems. And we basically plotted their exceptional points. And what we found was the following, which is actually well known in the open systems literature, that these eigenvalues, if you plot the eigenvalues of these non-Hermitian Hamilton describing this 1D chain, you can with very reliably tell what is the regime of weak coupling, which is shown with the hashed line, and what is the regime of strong coupling. But you actually do not get any information about what happens in the strong coupling. When you have multimode system, what is strongly coupled to what? Is it A2 which is strongly coupled to 1 or N is coupled to 1? You just know that you're strongly coupled. And plus, so you don't get any fine-grained information. So that was the issue. And in the spirit of time saving, I will skip these slides. But the punchline is that the usual idea of mode indistinguishability, when we think about entanglement, you should not be able to see what is Alice, what is Bob, or even Clark when two things are strongly correlated. It doesn't, you can't really distinguish them. That kind of mode indistinguishability ideas do not work in open systems. In fact, even at EPs where everything is degenerate, not all modes participate equally. That is the main issue, that you can't just naively think about mode indistinguishability as a sign of diagonalization. So we actually what we found, which was actually quite nice. Again, this is the idea of having local observable, some kind of a joint, but semi-local observable. If you use pairwise indistinguishability checks, then you can actually make a complete map of correlations in the full parameter regime. So in fact, what we found was that if your pairwise correlations form a closed subspace, that means that you have actually generated a higher order correlation. So let me actually go to the next slide, which will make it clear, because again, I'm running out of time. Let's say this is a 3-mode system, which is like you have a chain of 3 atoms. And you are trying to actually find their exceptional points. So the exceptional points are B, C, and A. But what happens in the strong coupling regime? When we actually do this pairwise indistinguishability checks, and we actually have to use eigenvectors, not just eigenvalues, what we find is in the region 1, it's actually 1 and 2 which are strongly coupled. In region 2, it's 2 and 3 which are strongly coupled. In region 3, both 1 and 2 and 2 and 3 are strongly coupled. And a true 3-way correlation only develops at a single point. So in fact, using this, we were able to actually find a diagnostic, which actually tells us when does a multi-mode system, many-body open system enters the strong coupling regime. And we actually use this ground state Cooley problem to actually to verify our findings. In fact, there's this really interesting thing which we found when we extended this to 4-mode systems. Well, this is the first point is, of course, kind of obvious that strong coupling is commutative but not associated. Just because 1 is strongly coupled to 2 and 2 is strongly coupled to 3 doesn't mean 1, 2, 3 are strongly coupled, which is what we know from here. The triangle is different from 1 to 2 and 2 to 3. The other thing which we found, which is actually something which is seen in quantum chemistry, is super exchange type phenomena. That if you have a very weak coupling between 2 strongly coupled subspaces, you actually can generate a larger connectivity map of strong couplings. But the more interesting thing is that now one can ask, is this a 4-mode correlated system? And the answer is no. Why? Because they have to form a closed subspace. And when do 4 modes form a closed subspace? When they have 6 connections, and this has only 4 connections. Because 1 and 3 and 2 and 4 are still not coupled. So in fact, in some sense, a triangle is more powerful than a square when you think about many body correlations. So in fact, using this eigenvector diagnostic, we can actually do a full characterization of both the coupling depth, which is the correlation weight, what is the kind of correlation am I developing? Is it a true 3-body correlation? Is it a true 4-body correlation? And the connectivity of the physical system. So for example, a square has a connectivity of 4, but a coupling depth of 2. Because it's never able to, it never forms either a triangle or a complete square vertex. So I'm going to actually conclude with some of the new directions we are pursuing. I hope I have given you some brief taste of the kind of engineered quantum systems, what they can get you. We are right now in the process of extending these ideas for multipartite and higher dimensional entanglement generation. And we are also working inspired by work from Albion and Vijay, how can non-Markovinity play a role in multi-photon nonlinear and dissipative systems. And now the question is, yes, we have a way to think about correlation maps of many body systems, but now we have to find a way of what type of correlation is truly quantum. Unfortunately, the metric we have developed is not sensitive or at disentangling classical and quantum correlation, but at least it tells us where to look for in the parameter space. So with this, I'm going to stop and thanks again for your attention. And I'll leave you with this acknowledgement slide. This is the names of all the people who do all the hard work. And we are hiring. So please, if you're interested, please apply for postdoc and graduate student positions. Thank you.
Thank you. I will stop the recording.